Hello everyone. I'm gonna demonstrate the lifting analysis of a structure that I've already created in SpaceGas software. SpaceGas software is a structural analysis software that is widely used in Australia. As you can see, the structure is built. It was a transporter structure for this piece of equipment, and the objective of the lifting analysis was to ensure that the structure is strong enough during the lifting. It's not gonna fail or overstress or anything. uh, right now this structure doesn't have any support, and it shouldn't have because we are going to lift it. So during the lifting the only support is the crane hook, of course. So what I'm gonna do, I'm gonna add slings or add straight members to these lifting points, which are highlighted as green. And as you can see, they're right now coming up with the default number one cross section, but I'm gonna change this cross section into something more suitable, which I've already created. It's named cable. It's a round section. uh, what's this? A round section with a 25 millimeters diameter. You can use your own uh, suitable sling, or um, and for the material I have already created a cable material with a realistic sort of Young modulus, and also zero mass, which is very important to have zero mass for cables because we don't want the COG of the lifted item be affected by the weight of the slings. Another important thing is that the slings should only demonstrate axial force. Therefore, we have to release all the moments at the end of the slings. So you can see at the first end I released only Y and Z components of the moment, and for the other end I released all three components of the moment. This way, this sling members or cable members will only have axial forces. This is a hook point, and at the hook point I only add fixed restraint. This is fully fixed, but because all the sling members don't have any uh, moment, there won't be any moment here. There will be only forces at this point. But for the stability reasons, we have to completely fix this point. As you can see, I fixed all the um, XYZ translations and also XYZ rotations. Uh, this model is not ready for analysis yet, because if I analyze it, it is very under restraint. It will say instability around rotation, whatever, which shows that this is under restraint and I have to restrain it. However, during the lifting we don't have much restraint, but what we have is our toggle lines, or the places that where we connect soft slings so that we can control the item in the air. In order to model them in SpaceGas or in any computer program, I normally use soft slings. And how I model soft slings is by soft springs. So basically, I model soft springs at four corners. Uh, I normally choose four corners because I know that this way I can completely stabilize it, and I apply very small stiffness. I normally apply 0.05 kilonewtons per meter stiffness at X and Z, which are horizontal directions. Of course, if you have different units or your software has X and Y, for example, horizontal, you have to do it accordingly. Now my model is ready for analysis, so I can analyze it, and we will take a look at the reactions. And what we see here is a vertical reaction which we expect to be there, but relatively big horizontal reactions at the hook, which is not possible, not realistic, and also at the soft springs. And the aim is to move the hook over the COG so that all of this horizontal reaction disappears. It's important for a lifting analysis to know where your COG is. You can do it by calculation or by any other means. In this particular case, which we have, all our masses are actually modeled. They are not forces, they are actually modeled masses. I can easily get the COG from the output. Here's my COG, and of course only X and Z of the COG are important for me. The Y component is not important because the Y component is totally depends on the angle of the slings, which should be around 60 degrees horizontal. So I'm keeping these numbers and I'm moving this point to a position where it is completely above the COG. There we go. So now my hook point is right above the COG, and if I analyze and look at the reactions, you see those huge horizontal reactions are just gone, only very small reactions remaining. If we want to make it even more accurate, I have to move the COG in the opposite direction of this reaction so that it actually disappears. So now that this force is towards the positive X, I have to move this point slightly towards negative X. So what I do, I'll add a small number here, and by try and error, let's see where it goes. Yeah, didn't have much effect, so I put 2. That was too much, so I put 1.5, and hopefully this time it should be okay. There we go. We don't have any further horizontal reactions. Our soft springs are kind of idle, they are not taking any load, and my hook has got only vertical force to 2-digit, of course, and that's accurate enough, I believe, for this analysis. And if we look at the deflections or deformation, you'll see there are pretty reasonable deformations here in the structure that now we can rely on. Another important thing that we have to check is the bending moment in the slings. So we see that there's no bending moment in the slings, so basically our release worked well. And also, of course, shear force, we don't have any shear force, and axial force, we have axial force in the slings. And this way we can see our lifting analysis is done, and we can even design structural members or steel members. We can see my utilization of steel members or load factors are all given, and this result is actually reliable and realistic, a simulation of the lifting operation. Thank you.